Everybody, welcome to our February webinar. We have Jason Gillham today, who is our CTO, COO, and co-founder at Impossible Metals. And take it away, Jason.
Yeah, Brian. Thanks, Holly. So appreciate everyone joining in. What I'm really keen to kind of chat a little bit about today is how we've taken some of our developments to date, and we certainly see lots of applicability for this and unique technologies we've developed for specifically collection and of the quantities of polymetallic nodules, but because there's been some unique things that we've been able to develop along the way, we're seeing opportunities for this technology beyond specifically the application that we're initially developing the vehicle for, but also for some secondary applications, both specific to deep sea polymetallic nodule exploration and scientific work, but then also applications beyond that. And so I'm going to give a bit of an overview of where we're at, talk a little bit about some of our thinking in that space, and then we'll undoubtedly have lots of time for questions as well through this. So first off, just to give a bit of a refresher on our roadmap and talk a little bit about where we have progressed to. So in May of last year, we were able to basically demonstrate our Eureka I proof of concept system. This was our shallow water, low payload system that incorporated some of the key technologies that were incorporated into the system: the selective harvesting, the vision system, and the buoyancy engines were all integrated into that system. And then very quickly after that, we started to build our Eureka II system. This is our first deep water system, slightly increased payload, slightly increased number of arms on that vehicle. So that has progressed. And now we're into our starting the design of Eureka III while we finish some of our testing work with Eureka II, and looking to test Eureka II in open ocean this year, and then moving into to Eureka III very quickly after that. So this is just some of the pictures from testing towards the end of last year of Eureka II. This is at two of our different test sites that we use, both in Georgian Bay, which is part of Lake Huron, here near our facility that's close to Toronto, amongst the Great Lakes. One on the left, you can see the vehicle just either being lowered or it looks like it's coming out of the water. And then on the right, where we get a bit of icing over in the harbor that we clear away to progress some of the testing work that we've been doing. And so just to introduce some of the components and talk about what all is incorporated into Eureka II. I know some of you may have seen some of this build up before, but just as for those who haven't, and as a refresher for those who have, it's a good way to kind of understand all of the parts of the system and how they all build together. So first off, the delta arms, and so this is one of the more innovative sort of enabling technologies that we've brought from a development standpoint. On Eureka I, there was a single delta arm. Eureka II, there are 3 arms on the bottom of the vehicle to pick up the nodules. Once those arms pick up the nodules, they set them into a conveyance system that pulls them up into the hopper. And so the conveyance system and the hopper is all shown in green. Then the other key enabling technology that's really important, because we're adding these nodules and adding mass to the vehicle as we're traveling without touching the seafloor, without touching the sediment, we need to offset that weight without thrusting down and causing all sorts of sediment disruption that way. And so the buoyancy engines these are the 4 buoyancy engines that are integrated into the system that gives us that offsetted weight as we travel along, collecting nodules. The next thing that shows up are across the front. These are three cameras, three stereo cameras that are integrated into the system. That's what the system uses to identify the locations of the nodules, to identify potential life that is observed, avoid the life, pick up the nodules, and also help navigate the vehicle over the seafloor. In addition to the cameras to aid in navigation and data collection, there's a range of other sensors. There's a combined fins and Nortec DVL that are integrated with the system, some forward-looking sonar, acoustic beacons, and radio modems, as well as environmental sensors that aren't easily shown on here. But there's a number of environmental sensors from standard CTD through to turbidity sensing that is all integrated into the system. A couple drop weights that are on the side to help with emergency recoveries. The battery comes up through the middle, stays low on the vehicle, but is in the middle, kind of nested amongst the hopper. The next thing that came in, you can see here at the center, is the control sphere. So this is the main sphere with the main brains of the system, and then there are a couple smaller spheres on either side that act as network distribution for the overall vehicle. And then there's a standard syntactic foam block along the top of the vehicle. A total of 8 thrusters, 4 horizontal and 4 vertical, integrated with the system. A stainless steel frame that will hold all of that together, and then some control surfaces to aid in efficient vertical transport through the water. And so so in terms of where we've got to with Eureka II, for the end of last year, we were operating the vehicle fully autonomously. We were achieving autonomous picking of nodules. We call them nodules. They're really lava rocks. That's what we use in the lake as our representative nodules. And then effectively conveying those lava rocks or nodules from the end effectors up and into the hopper and collecting them on the surface. So our next milestone is really what we're aiming to achieve in the first half of this year, is deploying Eureka II into the ocean and onto a real nodule field for collecting of real nodules. So the next thing to really kind of talk through is I want to key in on some of the key enabling technologies that we've built, describe them in a bit more detail, because there really are, the more I've talked about this with various people, there are always unique and interesting ideas for how to use these enabling technologies in additional applications. And then talk a little bit about the platform as a whole, and similarly opportunities that we've started to see for how to use the platform beyond what we're specifically developing for. So the first to talk about are the delta arms that we've developed. So on the left, that's sort of your standard, I think that's a 4-function or 5-function reach robotics ROV arm, and then on the right is a picture of the underside of our vehicle on the delta arm. And so that delta arm is one of the things that we are fairly proud of. And so where the standard serial robotic arms are high dexterity, high strength, designed for lots of range of motion and high precision, because it's a serial robotic arm, meaning that when the base joint moves, it has to move all of the actuators that are part of that arm. That makes it a heavier arm. It will move more slowly as a result. And that's where the delta arm becomes a useful tool for us in our application. So with the delta arm, none of the actual actuators are moving with the end effector itself. It keeps the end effector very light and able to be low inertia and have high speed. It similarly has high precision, but doesn't have the dexterity and the strength that a standard robotic arm has, but that we don't need for our specific application. And then the other key enabling technology is the buoyancy engine. And so some of the buoyancy engines that are more traditionally used on, say, a glider vehicle, those will have a fixed mass and variable volume, variable displacement, where they basically pump oil, expanding a bladder and then contracting that bladder, maintaining a constant mass, but varying the volume that mass is taking up. With our system, we have a variable mass, but a fixed volume. And so this schematic on the right is really focused on the schematic of the system, where we have a sphere that contains water in it, and then a pump. And so as we are taking on mass, we are pumping water out of that sphere to adjust our mass in the system. And so in this state, the mass will change, changing what the basic force of gravity is on that system, such that when the force of gravity is larger than the force of buoyancy, we're going down, and when the force of gravity is less, then we have an upwards force with this system. And really, this is what allows us to have substantial mass changes with our platform, and really have substantial payloads. It also is what allows us to navigate close to the seafloor, because with the buoyancy engine, we are able to maintain a slightly positive buoyancy to the vehicle at all times, such that the thrusters are maintaining a slight downward thrust at all times. That way, if we want to go up, we just reduce the amount of downward force from the thrusters, giving us a high bandwidth, high responsiveness for the altitude control, while never having to actually thrust down to kick up sediment. As anybody who has worked with ROVs down near the seafloor will know, that becomes a real challenge. And so this is my last slide, but I really want to talk through kind of what we see as some of the opportunities with the overall platform. So the first is some of the targeted sampling. One of the things that we see as interesting with this platform is the ability, because it has that payload capacity and an ability to go from location to location, having visual sensing of where it is located. It's able to very specifically target where a sample could take place and take multiple samples. So if somebody is looking to, say, sample within a track of where a vehicle had previously gone to do a collection operation, the targeted sampling could specifically look for the right characteristic of where a sample is needed, and then able to collect that specifically at that location. Also, efficient water column operations is something else that the vehicle is able to do. Because of the dynamic buoyancy, that's a very efficient way of traveling vertically through the water column. And so an ability to, again, move up and down through the water column, staying in location, but looking for certain signatures for where to either collect digital samples or physical samples, is another area where we see some interesting opportunities for the system. I like to sort of think of it in some ways as a vertical glider rather than a horizontal glider. The other thing that we're exploring and looking at and have had some interest in is using it as a box core system. The ability to free fly without having to utilize ship time to to allow ship time to go off and be utilized for other operations, while sending the untethered vehicle down for a box core is something that I think has some economic benefits and some operational efficiencies potentially in a real world situation. And then lastly, something that's interesting is the high payload capacity. Our Eureka II, as it is today, has a 50 kilogram in water weight for the in terms of its capacity, and able to stay neutrally buoyant while taking on that additional weight. But there isn't a fundamental limit to that, as ultimately in our later versions, we will be increasing that payload capacity. And so for high operations where high capacity lifting is required, or many samples are of interest, this becomes something that could be utilized. And then, as we briefly talked about already, that the idea of close seafloor operations, the ability to maintain a buoyancy that is slightly positive while close to the seafloor has some applicability for us. So with that, I didn't have tons prepared, but really keen for lots of questions. And I've seen a bunch of questions start to come into the chat already. Holly, I don't know what. I'll hand it over to you, and you can kind of facilitate asking things and letting me know where to take it. But you're also
my microphone on. We will go ahead and go through the chat questions first. But if you'd like to ask Jason a question, if you look in the center of the bottom of your screen, there's the hand. Go ahead and click on the raise hand, and then we'll just go through an order on that. All right, so let's start with the questions. So do you want me to read them, Jason?
That would be helpful, even just for everybody else.
Okay, so from Kirsten, she said, I thought you were out on Blake Plateau now to test Eureka II, or did I get that wrong?
Yeah, so our testing of Eureka II is an ongoing activity for us. We had some initial work testing our launch and recovery system, and then we'll be continuing to go out in the coming months and completing that sort of first scope in the first half of this year.
Great. Okay. George asked somewhere, I also read that Eureka II is successfully tested. Was that test conducted in tranquility conditions? And now I guess it will be tested in real situations.
Yeah, so there's to be specific about the conditions where we have successfully tested Eureka II so far. It's been shallow water conditions in the lake here in Georgian Bay, and so the range where we've tested Eureka II so far is down sort of in the 50 to 100 meter maximum depth range, but we've also one of the things that I'm looking forward to actually when we go to quite deep waters is the increased water clarity and the lack of ambient light for our vision system. That's certainly something that will be much easier for us as we get to the depths. And so the picking up real nodules is really the next step for us, and that's the first half of this year.
Great. All right. So then I'll call this a comment from Kirsten, but I'll go ahead and read it out. So responding to George, Kirsten said, Blake Plateau is off the North American shelf. Depth, I think, about 1,000 meters or so. Nodules present, but sediment conditions very different from CCZ.
Yeah. No, that's I think one of the next steps for us after real nodules becomes closer and closer to real sediment conditions. We've the internal to our shop, we have, and there's a blog post on our website a little bit about this, where we have what we call our 1 degree of freedom test stand, and that's where we've really iterated through different end effector designs and we will progress to iterating through different sediment types and structures. But I'm also well aware that there's nothing quite like the real conditions in the CCZ in terms of the sediment that can exist there or in other fields beyond in addition to the CCZ.
Great. All right. Then we have a question from Levi. If each nodule essentially has some bacterial life / biodiversity on its surface, what's the point of picking up nodules individually? What are the parameters you're using for assessing life? And is this only available in CZZ, or is it going to be used in hydrothermal vent regions?
So our, and I'm sure there's others on the call who understand the different resource types better than me, but just to kind of give my understanding of kind of from a high level, different resource types that exist. There's the seafloor massive sulfides or vents, which you're referring to. There are cobalt crusts. That's what I believe is predominant in Norway, which opened up their region recently. And then there's also the polymetallic nodules. Our focus is only on the polymetallic nodules. We have no plans to explore crusts and seafloor massive sulfides or vents. And then in terms of bacteria on the nodules, our vision system is what we're using to identify life on and then have an exclusion zone around anything that we've identified. And so the vision system is not able to see that we're picking up the bacteria that's on the nodules, and therefore won't avoid picking those up. Our intention, and really what we're doing some work with scientists, and we need the information from scientists, is to understand what is the percentage of nodules that we can pick up, recognizing that there is some life and bacterial life that's getting picked up on these in order to maintain ecosystem function. That is the sort of the threshold that we're talking about internally as what's important to achieve, recognizing that, yes, some things will get either inadvertently picked up or just not able to be observed, and therefore will get picked up. But really maintaining ecosystem functions, what's important. And because we have the ability to leave a percentage of nodules behind, leave habitat corridors behind, leave a distribution of the nodules, we're certainly expecting and hopeful that we can selectively harvest the nodules in a way that achieves that.
Great. Tristan, you had a couple of questions. Would you prefer to ask them versus me reading them?
Actually, my next one is not hello to everybody. Sorry. Maybe I should. I'm a deep sea ecologist, and I've spoken to Becky several times, Becky Uhlet, and I'm actually looking now at the legal landscape of deep sea mining and find that hugely fascinating. So. Yeah, my question is actually rather about the box core design that you're thinking. And I've got trained. I got my first really deep sea experience on box cores. And in the Indian Ocean, I sift, I don't know how many box cores down to the bottom. So I know how blimmin' heavy these things are. And also how difficult it is to get an undisturbed sample up there, because it depends for what purpose you want to take the box core. And as a biologist, you want the surface of the box core as undisturbed as possible, so you can still identify Lebensspuren, so the traces that animals leave behind. So you can make the connection between those traces, and then once you slice the core, we call it core slicing, with a trowel, you call it?
Yep.
Is that, yeah, with a trowel, first centimeter, second centimeter, and they all go in different buckets, and then you sieve it, and so you know which animal lives where. So how can you with your design, pick up a box core and make sure that the supernatant water is as little disturbed as possible? And how big? What is, most box cores that are used are 50 by 50 centimeters. That is kind of the standard, which is, fairly chunky. Maybe you can.
Yep. So
ideas.
Yeah. So I mean, and so to be really clear, there isn't this isn't a thing where we have a solution that's absolutely defined. And so that's part of what I'm really keen about, actually, this conversation. And so, but to talk through some of the thinking in achieving it as undisturbed a box core as possible. My understanding today with the more cable-driven, gravity-fed box cores, there's a somewhat substantial bow wave that precedes that and can cause some initial disturbance even before the box core has engaged. And so
what you normally do is, actually, when you lower the gear, you have obviously some pinger on the system, and then before you reach the bottom, the winch would stop and you would let it, kind of slowly come. And then you try as far as possible, as you can do as a winch driver, being 6 kilometers or 5 kilometers away, lower it gently. But yes, there's that. I was actually also concerned about when you bring it up.
Sure. And I was just going to want to talk through about the whole process.
Yeah.
So there's a couple pieces to this. One, because we have very precise buoyancy control, the ability for us to have that extremely gentle set down, I'm hopeful that is something that ends up being achieved as we look into this further. And so by very gently setting down, that's sort of that first step of getting there with as little energy as possible, because the more you start to put energy into it, that's going to just disturb things. And so the next piece then becomes kind of that, what I'll call the cut, where we end up having to actually engage, and what that mechanism is and how to make that done right. Because my understanding, actually, with the cable-driven ones, some of that is based off of just the inertia and gravity of the heavy device getting.
I mean, it's you have the frame around it, and the frame remains, that is loaded down, that remains on the sediment surface, and not the frame is way down above the box core, so the weight of all those lead blocks that drives the box then into the sediment.
And so using the adjusting the buoyancy again gradually to allow that to sink in in a controlled way is my hope on that. And if something is needed that's a little bit more explosive, then we may have to go that way. But that becomes the hope, and then that becomes a captured sample. And we are able to then reverse that process to very gradually get out of the sediment and then travel up in a controlled way, keeping that sample contained to then recover it onto the deck.
Contained also on the on the surface.
If that becomes part of the requirements that become beneficial, I see that as something that could be absolutely achieved, because
that is one of the problems. When you pull the box cores are usually open.
And so that would be something that could be, because there are additional actuation capabilities, we can have an actuator that would close the lid, and so after it has been captured, the lid can get closed and it can be brought to the surface in that undisturbed way.
Your advantage is also you can bring it up faster, because that's another problem. The cable being so slow,
interesting,
the sample warms up in trophic waters and the animals can't. But I'm hogging whatever. I'm taking over the conversation. We can have that on the side.
I appreciate it, Kirsten. Thank you.
All right, Tristan, You are on mute.
Oh, sorry.
No, not at all. Thank you, Kristen. Those are great.
Right, thank you. Jason, I've got, I think, three questions here. I did try and type them into chat, but yeah, I'd like to ask you specifically. My background is in AV design and operations for 20 years, so altitude control at 6,000 meters is going to be hard. How do you plan on doing that precisely? Like, and also what kind of range of altitude control do you need to maintain for your manipulator arms to still be able to pick up the rocks?
Sure. So our altitude control comes from two primary input sensors. The first is the array of stereo cameras that provide sort of millimeter level accuracies of what our actual altitude is, and then there's acoustic. So acoustic will give us altitudes as we approach, and but ultimately when we get down for
no, that answers my question, because yeah, you can get close without acoustic, but you can't do millimeter level with acoustic. So it's stereo cameras.
Exactly. And then we require sort of 5 centimeter accuracy or consistency of altitude in order that gives us the range of motion that the arms can accommodate.
Okay, that's much bigger than I assumed. How do you, and maybe you've done it in a previous demonstration, but how do you pick up the nodules off the sea floor and then move them into a hopper mechanism that's at a different vertical from the sea floor?
Sure. So it's there is, and it wasn't shown on that initial animation because we didn't have it when we developed that, but there is basically we call it a scoop, and so there's a tray that has that the arms drop the nodules to. That's at a similar level to that, and then they through suction get pulled up and into the hopper.
Okay, so most of the arm motion is lateral.
Yes.
Okay. That makes sense. Thank you. I'm not sure it's appropriate, but in your previous public information, you've listed the cost or assumed cost of buoyancy spheres in one of the worksheets, and that really caught my eye because I think the line item was like $1,800 a sphere. And for your Eureka III, you're talking about needing 500 spheres per vehicle. Are those numbers still ballpark right?
That ballpark sounds correct, except for so Eureka III, we have done some work to likely reduce the size of that. So our expected size of Eureka III will be reduced from what our sort of maximum economics are, but likely be competitive with dredging-based solutions. And so rather than a 25-ton capacity, we're looking at about a 6.
Okay, because I'm again really surprised at that, because you know I've designed and built VBS systems in the past, and the cost of the titanium spheres was an order of magnitude, if not more.
Yeah.
So have you got some kind of new sphere technology?
Yeah, so the spheres is one of the key, and the design of those spheres is one of the really key aspects of IP that has enabled us to achieve the economics that is relevant.
Okay, well done. You might be I think a new business opportunity is selling those spheres to everybody else in the industry. I think that was my main questions. Thank you very much. Appreciate that.
Yeah, thank you.
Thank you, Tristan. Okay, I'm going to read Usman's question that was in the chat. Eureka II is in testing phase and was developed late last year, but the fleet will be produced slash pushed out in the market starting next year. What are your plans for change control / obsolescence management for the parts which come to an end of life from OEMs?
So yeah, bunch of interesting stuff there. Our focus on so just to make sure we're clear on timelines here. This year is when we expect to have Eureka II fully demonstrated, and we'll be starting on building of Eureka III. Eureka III will have demonstrations in next year, 25, where we are looking to then be in a position to collect materials with a fleet in 26. So just to make sure that timeline is understood. On the sort of plan for obsolescence of components, the systems we've built to date are all about proof of concepts. We have not had a stringent internal manufacturing controls for what has been built. That will come later, and with that will come a plan related to obsolescence of parts combined with preventative maintenance, and ultimately that is optimized with really two things being considered. One being the maintenance and economics of it, but then also just the environmental aspects of over upgrading of components and making sure that we are disposing, fully utilizing components and then disposing of components within the system in a responsible way.
Great, thank you. All right, I'm going to read Levi's question next, and then Kiran will go to you after that. So Levi asks, how do you offset the water from harvesting the nodules? What happens to the water stuck in the nodules? Does it get dropped back into the ocean? And if so, how deep does the discharge go?
There isn't a specific, so because we don't have a riser pipe system where we are pulling up a lot of water with the nodules, the degree of discharge is not the same as your typical riser system. There will be some water entrained within the nodules when they come up, and so they're exactly what that dewatering system is, and if a discharge would be required for that is not something that I have a great understanding of at this point. Our current plan is not to have a discharge, but because we haven't fully defined what our any sort of entrained water dewatering is within the nodules, there is a question there that's absolutely legitimate.
Great. All right, Kiran.
Okay, can you hear me now?
Yes, we can.
Okay, thank you again. Thank you, Jason, for providing us real good information, and also I learned a great deal from the questions. Coming back to the theme of your presentation, if Impossible Metals is looking for, application of your core technologies elsewhere, is there any plan to reach out to Triton Subs, WHOI, NOVA, or DOD, and give them a presentation just as to what you are doing?
Yeah, so we're in the early stages of exploring some of these secondary applications. Our initial interest is to explore secondary applications specific to sort of the deep sea mining community, and focus within that community, as that's where our focus needs to be. There are we have some of our investors that have some degree of connection in line with interests for secondary applications, and so down the road we may start to explore that, but we also just as a company need to be mindful of maintaining focus as much as possible.
Thank you.
Great. All right. Any other questions? Okay. Tristan, you want to ask?
Sure. Yeah, I was just saying, if time permits, Jason, the launch and recovery of AUVs at sea is always problematic. It's when vehicles get damaged. Yeah. And so, your presentation, sort of the company presentations about the future state of sustaining a sortie rate of like 6 vehicles or more a day out in the open ocean seems extremely ambitious to me. Can you talk a little bit about the technologies that you're working on for that autonomous homing and docking into a heave compensated crane?
Yeah, perfect. So still in a conceptual phase with some of that development that really will be kicking off. We see in the second half of this year. The core focus for us is the concept that is currently sort of taking center stage for us in our minds through any of our discussions is what I'll call a dual crane system. And so these would be two cranes that work in concert with each other. The first that really just controls a capture basket. That capture basket would get placed below, and so this crane is more akin to a robotic arm that would reach the basket below the water's surface, below the wave affected zone. The vehicle would come up and into that, and through a combination of that crane and the vehicle's motion, capture the vehicle below the water surface. That crane would not, because it will be designed for a little bit higher motion. It won't have the strength to lift the payload that we're seeing with these vehicles. But that's where the second crane comes in. So that would be a cable connected to that basket that takes the vertical load and pulls the vehicle from the water while it stays stabilized from the first crane through the lifting operation.
So it's somewhat similar to an ROV cage system.
Exactly. Right. So it's the idea that it says come into an ROV garage below the wave zone, and then your operations can become similar to a standard TMS recovery at that point. Okay.
And what are you sort of assuming for amount of downtime due to damage in that process?
Yeah. So we have about a 15% downtime expectation. I believe that's what it is in the model, where we then offset that with some additional capex. Because we have a highly parallelized system, the intention is to maintain upside by pulling spares in to the process wherever possible.
Thank you.
Great. Okay. Kirsten had. I'm not going to say that's a question, Kirsten. So, did you want to? Yeah.
Oh, only. I mean, that might be more, for people who are interested in the biology. But there was a question earlier on about, Jason, you said you need the input from the scientists about, how many nodules to leave behind. And basically, that's not known at this stage. The ISA, as you probably are all aware, they've set up three development groups for thresholds, or expert groups for thresholds. But ecosystem function is unfortunately not one of the things these groups look into. Yeah, it's very tricky to say. It depends so much on the life history of the individuals growing on the nodules. For bacteria, I don't see much of a problem, to be perfectly honest, because bacteria are pretty, they are the first step. You need a biofilm on any surface before anything else can grow there. They're partly in the surrounding waters. They should come back relatively quickly, but any bigger animal like sponges or corals or whatever might grow as a filter feeder on these nodules, that will take more time to return. Plus, the more, shall we call it, desert area around it, the more area around it devoid of nodules, the further the propagules have to travel. And they can't travel against current, for instance. So yeah, all these questions have to be taken into consideration before we can come up with any kind of recommendation there. It's a bit trial and error in the first stages.
Good, thanks.
All right.
Can I comment on that?
Sure.
Well, one of the things I've been quite impressed by the Metals company doing is that the amount of funding they've put into the science, right? So I'm assuming someone like Kirsten who goes out and actually tries to answer some of these fundamental questions that we as a species don't know. And they've put at least 75 million into funding that research in order to, answer some of these fundamental scientific questions, and also to gather the baseline data they need for an environmental impact statement. So my question is for Impossible Metals, what are you doing in a similar vein? Are you funding scientists? How do you keep the impression of industry funding science from tainting the science? And
sure.
it's all sort of related. Like, it's not just one question there. It's a whole big conversation, right?
Yeah, and I'm not the best person internally to answer and address some of that. Our focus is predominantly, however, technology development over site exploration, and so I think a lot of the science is being done, say with the Metals company within their tenements and by others within their respective tenements. Our focus has been on engaging scientists and looking to provide a technology to collect this in a way that allows us to take everything that is being learned in those areas and be as responsible with it as possible, while still maintaining economics for industry.
Tristan, I mean, those companies only do that because they have to. I mean,
Well,
if you read,
that's a cynical view, but I mean, I think for me personally, there's an element of let the science speak, right? And I've been following along the debate, and it seems like some of the more vocal anti-deep sea mining voices are actually shutting down or misinterpreting some of the scientific results that are coming out. And so, I'm very happy to have someone like yourself, Kirsten, talk about, what questions would need to be asked and what data you'd need to see to be able to come up with some kind of recommendation, like, what percentage of nodules should be left behind? Is it 100%? Is it 95%? Is it 5%? These are big deltas, right?
Oh yeah. And we can only answer those questions with the contractors.
Yeah.
Because science, without that, I mean, because of the science that has been done for exploration, that is, the reason why we know actually quite a lot about the CCZ now. Yeah. Without that we wouldn't have that knowledge, because no government can fund that.
Exactly. Yeah. So I think there's an opportunity here for a harmonious blend of these interests. I think either extreme, it should be, I'm a very pragmatic person, right? So anything that's extreme is automatically almost discounted, right? So the voices that are saying, just ban deep sea mining outright, don't even think about it. It's like, well, let's talk about the impact of land mining and all the rest of it, right? And then the voices that are saying, yeah, but think about all the money to be made. We've got to do it no matter what. It's like, oh, hold on a second. No, the environmentalists and the biologists are totally right. We can't go in and destroy another ecosystem. But there has to be a viable middle ground, or at least we need to gather the knowledge using robotic technology, offshore technology, to be able to answer those questions. So, I think what Impossible Metals is doing here in terms of being able to sample individual rocks and have the stereo vision system that can discriminate between rocks that have life on them and rocks that don't is a really interesting concept. And, I'm pretty excited to see what you guys get up to.
I appreciate Tristan. That's well said, and I think that's as you put it, pragmatic or kind of practical view. So wonderful. Anything else that we can chat about? Otherwise, I'll let Holly wrap things up.
Yes, Levi, there is going to be a recording of this meeting. I'll get it today, and I'll probably send it out on Monday, the link to it. So that'll be for anybody who registered. Looks like Ray has a question. You're on mute, Ray.
Can you hear me?
Yes, now we can.
Yeah, hi. I'm wondering if there's obviously a consistent theme with environmental concern. I'm wondering if there's a way to sort of highlight, whether it be on the website, sort of the more commonly asked questions. I haven't seen all the webinars, but I've seen a few of them, and it seems like there's a common theme that comes up. So I'm wondering if there's a way to list commonly asked questions, or, you know, please review this before asking questions related to environmental concerns, or I wonder if that's of any value.
Yeah, great. Thanks, Ray. We'll, I suspect we'll definitely have, that'll be relevant. Holly will probably put it on our list for next
Yeah.
marketing meeting, and
Yeah.
there's some opportunity there for sure.